Hello, this is Dr. Joe Trout from the physics program at Stockton University. And this lecture is on asteroids and comets, and it's chapter 13. So this chapter 13, comets and asteroids, the debris of the solar system. And if we look at comets versus asteroids, the main difference between asteroids and comets is their composition. Asteroids are made up of metals and rocky material, while comets are made up of ice, dust, and rocky material. Asteroids form more closer to the sun, where it's too warm for ices to remain solid. And comets formed further from the sun, where the ices would not melt. And comets, which approach the sun, lose their material with each orbit because some of their ice melts and vaporizes to form a tail. So we have to see Hale-Bopp, that was one of the most active and easily visible comets during the 20th century. And it's shown here as it appeared in the sky in March of 1997. And you can see the comet's long blue ion tail, and the shorter white dust trail. And you'll learn about these two types of comets and how they form in this chapter. So the asteroids in the solar system, this is a computer-generated diagram, shows the position of asteroids known in 2006. The asteroids are not drawn to size and were drawn to scale. If they were, none of the dots representing the asteroids would be visible. Here, the asteroid dots are too big, and they give a false impression of how crowded the asteroid belt would look if you were in it. Note that in addition to those in the asteroid belts, there are asteroids in the inner solar system and some along Jupiter's orbit. And they're controlled by the giant planet's gravity. So you see you have a lot of asteroids here, and then the Trojans and the Greeks that pretty much exist around the Jupiter's orbit. So if we look at where the different types of asteroids are found, we have asteroids of different compositions or distributed at different distances from the sun. So don't forget, this is an astronomical unit, and it's the distance from the sun as we move out. And we say that the S and C types are both primitive, and the M types consist of cores of the differentiated parents of both. So we have the S type, or the stony or siliconaceous, and we have the C type, or carbonaceous, and the metallic type. So this shows how many there are and where their distances from the sun, and we see how many there are in the distance that we move from the sun. So this is a piece of Vesta. This meteorite rock fell from space, and it's been identified as a volcanic fragment from the crust of the asteroid Vesta. Here we see three more asteroids, and this is Mathilda and Gaspra and Ida, and the first three asteroids photographed from spacecraft flyby and printed to the same scale. So Gaspra and Ida are S types and were investigated by the Galileo spacecraft. And the third is a C type and was a flyby target for the Near Shoemaker spacecraft. This shows the asteroid Ida and its tiny moon Dactyl, and it's a small body off to its right. And these were photographed by Galileo spacecraft in 1993. So the irregular shaped Ida is 56 kilometers at its longest dimension, while Dactyl is about 1.5 kilometers across. So a kilometer is about a sixth of a mile. So this is about almost a mile across. And the colors have been intensified in this image, so we could keep things looking, so you could see them easier. But notice it's the irregular shape. And once again, this is the idea that any mass, any two masses will feel a gravitational attraction. So when we have a planet that's orbiting another planet, it's due to this force of gravity. And here we see the force of gravity of this comet, of this asteroid, and causing this moon to orbit around it. Here shows two moons of Mars, and these two small moons of Mars, Phobos and Deimos, were discovered in 1877 by American astronomer Asaph Hall, and their surface materials are similar to many of the asteroids in the outer asteroid belt. And this leads astronomers to believe that these two moons were actually captured asteroids. So they were flying around in space, and then they were captured by Mars, by its gravitational field. Here we're looking down on the north pole of Eros, and this view is a construction of 6 images of the asteroid taken from an altitude of about 200 kilometers. So the large crater at the top has been named Psyche, after the maiden who was Eros's lover in the classical mythology. And it is about 5.3 kilometers wide. So a saddle-shaped region can be seen directly below it, and craters of many different sizes are visible. Here we see that the surface of this asteroid appears to have no craters, and astronomers have hypothesized that its surface consists of rocks and ice chunks held together by a small amount of gravity. And its interior probably is also of similar rubble, a pile of rubble. Here we see Hayabusa return, and it's a dramatic image of the probe breaking up as it returns upon its re-entry. And the return capsule, which separated from the main spacecraft and parachuted to the surface, glows at the bottom right. Here we see Vesta and Ceres, and the NASA Dawn spacecraft took these images of the large asteroid Vesta and Ceres, A and B. Note that Vesta is not as round as Ceres, which is considered a dwarf planet. And a mountain twice the height of Mount Everest on Earth is visible at the very bottom of Vesta. The image of Ceres has its colors exaggerated to bring out the differences in composition. And you can see a white feature in one of the craters near the center of the image. So this white spots in the larger craters, these features appear to be salt deposits, and which are about 92 kilometers across. We also see comets impact with Earth. So as the Chelyabinsk meteor passed through the atmosphere, it left a trail of smoke and briefly became as bright as the sun. And hundreds of kilometers of forest trees were knocked down and burned in the Tunguski impact site where it came down. So if we look at near-Earth asteroids, we see that the ones that are small, about a kilometer, we found since about the year 2000. And we found, and most of them have been found recently. And the discoveries of the near asteroids, the accelerating rate of discovery of these near-Earth asteroids is illustrated in the graph above. And it shows the total number of known asteroids and the number over 140 meters in diameter, and the number over 1 kilometer in diameter, and the size poses a dominant impact risk on the Earth. So here's one of the near-Earth asteroid. It's about 5 kilometers long and it approached within 3 million kilometers of the Earth in 1992. And this series of images is a reconstruction of its size and shape obtained by bouncing radar images off the asteroids as it during its close flyby. And it appears to consist of 2 irregularly lumpy bodies rotating in contact with one another. This is Comet Halley, and this composite of 3 images, one in red, one in green, and one in blue, show the comet's Halley as seen with a large telescope in Chile in 1986. And during the time, the 3 images were taken in sequence. The comet moved among the stars, and the telescope was moved to keep it image steady with the comet. So as the comet moves, we have to keep the telescope moving with the comet. So what you see is as this 3 picture was taken, it causes the stars to appear in triplicate, one in each color. This was Edmund Halley, and Halley was a prolific contributor to the sciences, and his study of comets at the turn of the 18th century helped predict the orbit of the comet that now bears his name. So if you look at the parts of a comet, this schematic shows the main parts of the comet. So note the difference in the structures are not drawn to scale. So the comet's actually moving in this direction. There's a dust tail that comes off of it in the opposite direction of its motion. And here's the comma. It's about 10 to the 5th kilometers. And then there's an ion trail that points away from the sun. So as this record moves around the sun, we see the dust in the opposite direction of its motion, and it spreads out as it moves away. And as the sun is driving the ion tail in this direction, the energy from the sun. Here's some captured comet dust. Well, it's believed that this particle seen through a microscope is part of a tiny fragment of a cometary dust and collected in the upper atmosphere of the Earth. And it measures about 10 microns. That's 1/100th of a millimeter. Here's a close-up of Comet Halley, and this historical photograph of the black irregular shaped nucleus of the Comet Halley was obtained by Giotto spacecraft from a distance of about 1,000 kilometers. And the bright areas of the jet are material escaping from the surface. The length of its nucleus is about 10 kilometers, and its details as small as 1 kilometer can be made out. Here's the head of Comet Halley, and here we see a cloud of dust and gas that make up the head or comma, and the Comet Halley in 1986. On this scale, the nucleus hidden inside the cloud would be a dot too small to see. So here's the comet, or the comet's orbit and tail. The orientation of a typical comet tail changes as the comet passes its perihelion, which is the closest part to the sun. And always as it approaches the sun, the tail is behind and the incoming comet head, but on its way out, it's actually ahead of the comets. So once again, it's always pointing away from the sun pretty much, but as it makes its turn, suddenly the tail is actually being forced out ahead of the comet's actual motion. So as the comet nears the sun, the features become more visible. And in this illustration from NASA showing the Comet Halley-Bopp, you can see a comet, the comet's 2 tails. And the more visible, easily visible dust trail, which can be as much as 10 million kilometers long. And the fainter gas tail, or ion tail, which is up to hundreds of millions of kilometers long. And the grains that make up the dust trail are the size of smoke particles. So the comet Micros was filmed in 1957, with a wide field telescope, and also shows a clear distinction between the straight gas tail and the curving dust tail. This image shows the Rosetta camera was taken from a distance of about 285 kilometers, and the resolution is 5 meters. So you can see that the comet consists of 2 sections with a connecting neck between them. So this is like one section here and one section here, and a connecting neck between them. In this close-up of the comet, another comet is from the Philae lander, and one of the lander's 3 feet is actually visible on the foreground. So these show gas jets coming from Comet 67P, and this activity was photographed by the Rosetta spacecraft near Perihelion. And you can see a jet suddenly appearing and only active for a few minutes. So here shows Chiron's orbit around the sun every 50 years, and its close approach being inside the orbit of Saturn, and its furthest approach out of the orbit of Jupiter. John Oort first suggested that there might be a reservoir of frozen chunks, potentially comet nuclei, that would come together and form comets at the edge of the regions of the sun's gravitational influence. And the first color images of the Kuiper belt object, informally named Ultima Thule, was taken at a distance of 137,000 kilometers from the New Horizons spacecraft back in January 1st of 2019. This is David Levy, and he's an amateur astronomer, and he ranks 3rd in the world for comet discoveries. Here shows the breakup of comet linear, and a ground-based view of a much less detail is shown in A, and B is a much more detailed photo of the Hubble Space Telescope, showing the multiple fragments of the nucleus of the comet linear. And the comet disintegrated in about July of 2000 for no apparent reason. Here shows a comet impact on Jupiter, and you can see a string of white objects or fragments of the comet Shoemaker-Levy 9 approaching Jupiter. And the fragment of the comets impact Jupiter with a point of contact on the bottom left-hand side of the image. And the bottom image was taken about 20 minutes later, shows the lingering flare from the impact. And the great red spot is visible near the center of Jupiter. And these infrared images were taken with a German-Spanish telescope. We can also see the impact of the dust cloud on Jupiter. So these features result from the impact of the comet Shoemaker-Levy 9 with Jupiter, and it's seen with the Hubble Space Telescope at about 105 minutes after the impact that produced the dark rings. So the compact red dot, black dot, came from another fragment. And the inner edge of the diffuse outer ring is about the size of the Earth. And later, the winds on Jupiter blended these features into a broad spot that remained visible for more than a month. All right, thank you for your attention.